In this chapter, we will discuss problems related to natural language processing and discuss some solutions. One example problem is, say for example, you're given a new text and you'd like to write an algorithm or an AI agent that will find out what language the text is written in. If we didn't know what language the text was written in, how can we learn from existing data to find out the language of a given text? Let us start by discussing the difference between formal languages and natural languages. Formal languages, that is the languages that we use to write computer programs like Java, Python, etc., can be very easily characterized by a set of rules known as grammar. We also call this syntax. On the other hand, natural languages like English, Spanish, etc., cannot be characterized as a definitive set of rules. Here's an example. Say, for example, person P1, says this sentence: "Thanks for dinner. I've never seen potatoes cooked like that before." So, this person P1 who said this sentence implies that he actually saw potatoes cooked, but he had never seen potatoes cooked in that particular way before. So in this sentence, if we look at the literal meaning of this, then it implies that this person has never seen any potatoes cooked. But the actual meaning is that he saw potatoes cooked in a particular way. Maybe he liked it. So for that reason, natural languages are many times ambiguous. Also, over time, the meaning of sentence keeps changing. For decades, one word may mean something, and after certain years, the same word can have a different meaning. For that reason, instead of deriving rules from natural languages, which we have tried for very long and have been failing, we instead build approximate language models. In other words, we build a model M1 for, let's say, language 1, let's say if this is English. Then we build a model M1, usually a probabilistic model that sort of captures the probabilities in that language. Then the question is, can we actually do this? Can we build models to sort of represent a natural language? If we can do this, say for example, we are successful at building a model, let's say M1 for language L1, then this can be used to classify text. For example, if we have unknown text and we don't know the language, if we have model, we can pass this text to this model and obtain the probability that this text belongs to this language. This model can even be used to generate new text because it will be a probabilistic model. One such language models are Engram character models. So what is an engram? Engram is a sequence of written symbols of length n. As simple as that. For example, ABC is an engram with n equals 3. For example, my name, Badri, B-A-D-R-I, is engram of n equals 1, 2, 3, 4, 5. So if we look at engrams of length 1, when n equals 1, we call such engrams unigrams. When n equals 2, we call those engrams bigrams, and when n equals 3, we call those trigrams. Now, we can imagine a language model for a written text as a probability distribution of engrams. Say, for example, I have a really long text, and what if I try to analyze the text, I will find out that certain trigrams or certain pairs of words or sequences of words will appear more frequently than others. Maybe the same word appears 1, 2, 3, 4 times here within these 4 lines. So this can overall be captured into a probability distribution where we can say this engram, let's say this character sequence XXX appears these many times, and another character sequence YYY appears so many times, and so on. So this can eventually help us build a table which can be used to compute the probability distribution. This is represented as probability of a character sequence C1 through N is the probability of sequence of N characters C1 through N. For example, the probability of the character sequence THE can be, say, for example, 0.027. Similarly, the probability of a character sequence, let's say ZZQ, can be very low. Now, this is obvious in the case of the language English, because such rare combinations of characters can have a very, very low probability. So essentially, an Engram character model is a model of probability distribution can be obtained from this frequency table of n letter sequences. Now, mathematically, an Engram model is defined as something known as Markov chain of order n minus 1. For example, a 3-gram model or a trigram model is defined as Markov chain of order 2. What this means is, in a trigram model, the probability of a character Ci depends on 2 previous characters. Say, for example, I have this sentence, "Thanks for dinner, I've never seen potatoes cooked like that before." We know that the probability of having this full stop here depends on all other characters before. I will know that I have to put a full stop here only if I know all the things before this full stop. Similarly, what should be the character here given all the previous characters? We can easily put an S if we know this English language model and given this previous input. What Engram character models use is the Markov chain of order n minus 1. What that means is, if we are using a trigram model to represent a language like this, let's say I have a trigram model, then it's a Markov chain of order 2. What that means is every next character only depends on 2 previous characters. In other words, say for example, if I know these 2 previous characters NE, I should be able to calculate the probability of seeing the next character V, and so on. So in general, the probability of any character Ci depends on all previous characters, that is, starting from character 1 to character I minus 1. But in the case of a trigram model, because it's a Markov chain of order 2, our probability of this character Ci only depends on 2 previous characters, that is, from characters I minus 2 to I minus 1. So that's what we mean when we say Engram model is a Markov chain of order n minus 1. Now we can define the probability of a sequence of characters C1 through N under the trigram model. So now we are specifically focused on trigram model, by first factoring with chain rule and then using the Markov assumption. What this means is, my character C1 through N, in other words, say I would like to calculate the probability of this sentence being in English. So then, using the trigram model that we have, we can say that the probability of any character C1 through N is the probability of that particular character given all previous characters. So the probability of T is, what is the probability given nothing? The probability of H is, what is the probability given T? What is the probability? The probability for A is, what is the probability given these 2 characters? The probability for N will be, what is the probability of N given these 2 previous characters? So in general, the probability of any character depends on all previous characters. But with the Markov chain, now for trigram models, we can say that the probability of any character Ci given an entire sentence is the probability of 2 previous characters. And what this pi sign means is a multiplication. What this means is this entire sentence has the probability of, let's say, probability of t given nothing times the probability of h given t times the probability of a given th times the probability of n given ha, and so on. So we keep multiplying this to get the probability of the entire sentence. Now, if we want to build our model, that is, when we say our model, we would like to list out the probabilities for all possible trigrams, right? Say, for example, I would like to list out the possibility of observing ABC, ABD, AAA, and so on. Then the number of entries that I would have in my model will depend on how many unique characters I have. Say, for example, I have 100 possible characters, including lower letters, small letters, and so on. That means that the number of possible characters that I will observe in the first position is 100, in the second position is 100, in the third position is 100 again. So that means I will have in my model, probability model, 10 to the power 6 entries. And if I have probability for all of these entries in my table, then I can compute all of these probability values and then sort of find out how likely this sentence is that particular language, or how much this sentence represents that language. Now the question is, how can we estimate this probability distribution? That is, how do we come up with a table where, say this is my model, and what I have is in my first column all of these possible trigrams, AAA, ABC, ABD, ABE, and so on. And let's say the probabilities for these are, let's say, 0.02, 0.1, 0.2, 0.001, and so on. So how can we come up with these probability values? That is the question. It's pretty easy. Say, for example, we are given a dictionary of this particular language. We can scan this dictionary or a lot of text in that language and then count how frequently each of these trigrams appear in this dictionary. And then we divide that by maximum or somehow normalize it to convert all the frequencies to these probability values. The next question is, how much data do we need to obtain such frequency table? The answer is the more the better. The more the better. Because if we have more data, then the model that we build, this probability table, will be more representative of that language.